what is our objective today? What we want to do mainly today is to prove two things. Firstly, to see the conditional expectation x given a sigma field G and an orthogonal projection F. Okay. And then orthogonal projection. So that's the first thing that we would like to do. The second thing that we would like to do today is prove the uniqueness. Okay. Existence and uniqueness of conditional expectation. Okay. In order to prove this, we're going to assume existence and uniqueness. The first property, we're going to assume existence and uniqueness, but later we'll basically show this as well. Okay. Why conditional expectation? And you will see actually that okay, one of the things that you can see when you are seeing this is that there's a deep relationship of this with the probability with the function analysis. That's what you're going to realize when proving these two things. And the second thing that I would like to emphasize that, previously I kind of gave you this course, but in other course discussions that we had on finance actually, that how you can price a financial derivative. Okay. So the basic principle is that you can price the financial derivative that give you, for example, a payoff X. In other words, this is the amount of money that you are expecting from a financial instrument like option or something like that. Okay. Then what do? You compute the expectation of this X actually, given a sigma field. Okay. And you discount it. Okay. This is what we call discounting, and that this becomes what you call the price of the derivative. Okay. Now this is something really real world that people uses in every day. Obviously they don't use directly this formula, but they use technology based on this formula. Okay, it's like machines based on this formula. Okay, in order to compute the price, the financial derivatives. Now what you can see from here that if I can price a financial derivative, it's depending on conditional expectation, which is a pretty abstract idea. So it's an orthogonal projection. So in other words, you can see this as an application of orthogonal projection into the finance. Apparently, orthogonal projections have nothing to do with money, but what you can observe, or what you will observe when you're gonna do a bit more things on finance, is that this notion is very practical. So when you are doing finance, okay, you are basically, all the time try to compute the conditional expectations. That's it. That's what you want to do. So that's what you call a bigger picture of math finances. That's what we are interested in. So give me some random variable, give me some information about this random variable, and try to compute its conditional expectation. And that is going to give you the price of that random mass attempt. Okay, not something that depends on that random mass. So these are very practical things. See them afterwards. So why I just emphasize on this, that what you can see is that this abstract orthogonal projection is doing something pretty much here. Okay. So let's move on to the first objective. I'm not going to go in detail but by L2 of P, okay, or sometimes L2 of omega Fp, okay. I mean, it's a collection of the random variables, okay, such that
absolute square integral
expectation of absolute
x square
of x square is finite. Yeah, square integral. Okay, so the integral of square of the random variable with respect to the probability measure is finite. Okay. So we discussed, some of the kind of things in function analysis. We're going to do more of this. What we can do on this, I can treat this at the moment as a vector space. It's a vector space. So I can define an inner product on this vector space. What do you think? What must be the inner product on this?
usual geometry over x.
Yes, so the expectation of the product of the random variables, which is simply the integral of x and y.
Excellent.
So what we can show is that with this inner product, this L2P is an inner product space. You can see from pretty much useful. Now I also know that this inner product induces a norm activity. And what would be the norm induced on this? Let's say denoted by the two norm.
The square root
Square root of expectation.
So it must be square of expectation of
Absolute.
are just taking
y to the
x and x actually. In other words, I can take this actually, so the product of x and x. Okay. And then what we can do, so we proved in our function analysis course, basic function analysis course, without getting into this theoretical measure theoretical stuff, that L2 space is complete actually. Okay. So on the same lines I can prove. So what I'm going to do in the next lecture, tomorrow, I'm going to basically prove that the LP space, okay, with respect to the any measure mu, where the P is in the convex domain, so it could be anything from 1 to infinity, including infinity, no, excluding infinity, okay, is complete actually. It's Banach space. I'm gonna, it's a Banach space. So that's what I'm going to prove. So mu is any measure, okay, and so I'm going to prove this result in general. Okay, so from this I can deduce that if I take P to be 2 and mu to be, okay, so for example the probability measure, okay, whatever the probability measure and like probability measure that you have in your probability space, then this L to P is basically a Hilbert space. So it's a Hilbert space. Okay. It's not only complete, but you have an inner product on it actually. In general analysis spaces you don't have inner product. So this is the result that I'm going to prove. In other words, I can show that this L to P, okay, is basically with two norm with the Hilbert space. Okay. If you want to see the concrete proof, especially for this case, I don't like the approach here, but almost in the sense that we're just focusing on this L2P space. So if you can prove a general result, why not to prove a general result and deduce this as a consequence actually? But you know, I mean, if you want to see the proof, you can see the proof from the book as well. So it's in the book. Okay? In chapter 4. Now, what I want to do next is I want to move to this objective that I want to see the conditional expectation as an orthogonal projection. So in order to present this result, I need to, just mention the result, and you have to just guess that we have proved all the results in function analysis. Okay, so you have to just try to guess that, okay, what result corresponds to, what is the result that we have proved is basically equivalent to the result that I'm writing here actually, in probabilistic sense. Okay, so let's begin. What I'm going to do, I'm going to take a random variable, a square integrable random variable, okay, from L to P, and I'm taking a G that is a subsigma field of F. Okay, and then we know from definition that this conditional expectation x given G is a G measurable random variable and satisfies an integral constraint actually. Okay, so we know this is P, at least in the sense of definition. Whether it exists or not, that's a different story. That's our objective, we can prove it. But if we assume that it exists and it's unique, then we know what this guy is. It satisfies certain properties. Then I would like to denote L2 G. So in other words, the probability measure that you have on entire F, okay, I can restrict it onto the probability measure on G actually. So in other words, this G inherits a measure from measure P from the its parent space. Okay, and obviously we can also show that this is complete actually. So why? Because this is an L2 space in its own. Okay, L2 space in its own. So what do you want? So L2 space is what? L2 space is the collection of all those random variables such that satisfies the conditions.
So this won't be the same map, right? This P, it would be restriction of.
Okay, it is going to be the restriction on the P, but I'm still denoting it by P. So there's no difference because it's the same. Are you getting the point? Then what can I show? Okay, let me throw things. I can show that it's a linear subspace. I think shouldn't be an issue. Okay, so it's a linear subspace, and so also it inherits inner product and norm and everything. Okay. In fact, I can prove a result. I'm not proving it, I'm just mentioning it. Is that this L2 GP, okay, is a closed subspace. Of L2
omega
FP or maybe L2 P.
size.
Why it must be a closed subspace? The answer is pretty simple, because I know this guy is complete.
Completeness.
So we have a result proved in
Closed subspace of a complete space.
yes, closed subspaces are complete, and complete subspaces are closed actually. Okay, so since L2 GP is complete, okay, why it's complete? Because it's a space of a satisfy a integrable function. The same argument would work actually that we use to prove that this is complete. Okay. So this is complete, and I know that any complete subspace of a Hilbert space, okay, is complete. Even a particle space is closed. Okay. GP is closed. Okay. So since this is true, so this must be true. And by the way, what I mean by closed, that for any sequence xn in
L2GP.
L2GP, there exists an x in
L2GP.
L2GP such that xn converges to x, okay, in this L2GP sensor. Okay. The argument would be simple, think about it. So if xn is a sequence here, convergent sequence here,
It's closed.
and this is a subspace of, so I can take a Cauchy sequence here. Take a Cauchy sequence, which is a Cauchy sequence here, and since same sequence is a Cauchy sequence in, what do you call
Parent.
The parent.
in the parent space, you're going to get a limit. But since this is also complete, so you're going to also get a limit actually. And what eventually you can show that the both limits are the same. Okay. So just a bigger picture, you want to see the proof, you can see it from here. Okay. Not spending time on it because we know all this basic stuff already. I would like to write a result, and you have to guess that what was the result that we proved while we were doing function analysis. The result is this, that if you have a closed subspace, of say L2 FP, and by the way, it's not something special about L2 FP, it could be any Hilbert space. Okay, could be any Hilbert space. Yes, any Hilbert space. Closed subspace of L2 FP. Then for any x, for any x in L2 FP, I can find a y, okay, in M such that the distance between x and y in 2 norm is the infimum, okay, of the distances between x minus z
That z
in 2
belongs
norm
to
such that z is in
L2 and Z.
okay. Have you seen something like this ever before?
Sir,
In
topology
your
मेरे
life?
ठो आज function distance minimizer क्यों है?
Yes, so it's like we proved what you call these minimizations result actually, and if you remember, we termed y as a minimizer of the norm actually, okay, or we can also treat y as the image of x under the orthogonal projection actually. Okay? So what is the relationship between x and y? So in other words, you have this space and I want to project it onto a closed subspace. Okay? So what you can do is that, okay, take an x from here, and since there are lots and lots and lots points in M, okay, out of all those points in M, see that which of the point is giving you the minimum distance actually, okay, and that point would be, what do you call it, minimizing point obviously, and is going to be the orthogonal projection of x
onto this end.
this point y in M. Okay? So if you wish, you can pick up your Marcus book and have a look at this result again actually. But since we have done it, so I'm not getting into it again. Okay, and if you want to recall the proof in probabilistic sense, so you can see it from the book as well. Alright. By the way, so there is an exercise, and this is something we also did in what do you call in our course. We basically denoted this map. I mean, if you remember, as for example BM actually. Okay, so P is the projection onto the M of the Hilbert space actually. That was our notation. Okay, and what we can prove is that if you have what? Okay, let me write it precisely here. So with the same assumption that let M be a closed subspace here of the S2 omega P, then if I take a y from M, okay, such that x minus y is orthogonal to 0, or is orthogonal to z. By the way, x is what? X is same as here. Okay. So,
For every z.
such that this is true, then
For every z in M, right?
I'm sorry?
For every z
For every z,
in M.
for all z in M, then the distance of x minus y in 2 norm is equal to the infimum of this set actually, x minus
Existence of the point.
x minus z such that in 2 norm such that z is in M. So can you comprehend what this in this statement are?
Sir, ये sufficient
what is the
condition है
relationship?
कि
I'm sorry?
sufficient condition कब हम project कर सकते हैं? Why?
So what we can do is this. So this statement is telling you that if you have a closed subspace and a Hilbert space, then for any point x, you can find a y that satisfies this condition. You can always do that. And I can, okay, so that's one result. So it's going to you can kind of, so this y is going to minimize the distance between the point x and the space M. Okay? And this second exercise is telling you, or maybe the result is telling you, that if you take a y from M, okay, under the same assumption, such that its distance, okay, so x minus y is orthogonal to z, okay, then this y is basically that minimum point, okay, such that x minus y is the infimum of the distance between the set point of the point x and the M actually. So in other words, what Fatah said is that he rightly pointed out that rather than computing this, I can easily try to find, for every x I can try to find a y for which this condition holds, for all z. And once this condition is satisfied, then this must be satisfied as well actually. Okay? Maybe you can give a try to this exercise. This seems that we haven't done this, but so it's kind of a replaces this requirement by a weaker requirement that just compute, take any x and try to find a y such that the difference is orthogonal to entire what do you
Closed
call
space.
Space actually. Okay. So in other words, this x minus y, I can say, okay, I can say that this x minus y belongs to the orthogonal perp of the element. So it belongs to the orthogonal perp of the element. Okay. So for x, you try to find a y such that x minus y is in the orthogonal perp of the element. Okay. And therefore, and it's because of this, you say that that for x, okay, for x, this nearest point y, this nearest point y is called the orthogonal projection. It's called the orthogonal projection. Okay. So what you are doing is that you are orthogonally projecting the entire Hilbert space onto a closed space.
So the way we used it, orthogonal projection was a map, right? Taking a point from the parent space to the subspace. But this is
I can say that for x, for each x, so I'm saying that if for all x there exists a unique y such that, okay, in other words, okay, there exists a unique y in M such that it satisfies this minimizing or maybe this condition that x minus y is orthogonal to Z for all Z in M and hence it satisfies the minimization condition. So for every x there exists unique y.
That function would
So now this is like defining a map x onto y as the orthogonal projection. Okay, orthogonally projecting x onto y. So that's what it's basically, and then it satisfies all those properties that you have that you saw previously.
linearity.
Okay. So once with this background, now I'm in position to prove my result that I want to. So what essentially I want to show is basically this. For a given x, the y that you are finding, it satisfies the both conditions. So it's G measurable, first condition. And if you compute its integral, okay, on any set B, then it is equal to the integral of x actually. Okay. So, and since you have a unique, what do you call, random variable that satisfies these two conditions. So in other words, I'm saying that I'm going to prove that y is G measurable. That's what. And then I'm going to show. Then I'm going to show that if I integrate y on any v from G with respect to dp, then this is same as x with respect to dp. Then what does this show? So this shows that this y is like behaving like the conditional expectation actually. But since we know that you have only one variable that satisfies these two conditions, then this y is basically conditional expectation. We are almost sure. Is it making sense? So I'm going to show that this orthogonal projection y satisfies both conditions. So therefore, y and conditional expectation are we are most sure. That's going to show that yes, I'm going to get the conditional expectations. In other words, probabilistically, this is true probabilistically. It's like that's the interpretation of this result in probabilistic sense actually. Okay. So in any other context you might get some other quantity, but in probabilistic sense what you see that for any x in L2 you can the orthogonal projection onto the closed subspace is basically the what you call conditional expectation. Okay. So here's a proposition that I would like to prove is that is that for any sigma field, subsigma field G of F, okay, it's not just a subset, it's a subsigma field, okay, and any